All right, let's talk about the fact that energy is quantized. And when we mean quantized, we mean that it comes in distinct packets. We talked last video about the fact that light comes in packets called quanta or photons. And we also know that the energy levels in electrons are quantized. How do we know that? Well, through an experiment called over a phenomenon called the photoelectric effect. So basically, what you do is you take a block of metal, which has a lot of free electrons, and you shoot light at it, and it shoots electrons out. Okay, so you fire photons at a metal plate, and it ejects electrons. You can detect those electrons being ejected. The problem is, if the light doesn't have high enough energy, no photons are emitted. And now this is related again. Remember, related to the wavelength of light. So light of a certain wavelength, it had to be of a certain wavelength or higher, or it wouldn't emit photons. Okay, so the photons had to meet some energy threshold, whatever that was. Then they found if they turned the brightness of the light up, so if they turned the wavelength down, right, they increased the energy of the light, the electrons would come out faster. They'd have more energy leaving, but the same number would come out. So turning the energy of the light up did not change the number of electrons being ejected. And also, if they had the same energy and just cranked the brightness on the light up, the intensity, so more photons, then you'd get more electrons at the same speed. So when they put these things together, they found, okay, so one photon can eject one electron if it meets the energy threshold. Otherwise, nothing happens. And the higher the energy of the photon, the faster the ejected electron, assuming it meets that threshold. So these results, the interpretation of these results, helped people kind of sort out what was going on here. And it led to this idea of this wave-particle duality of nature. So all waves travel in discrete particle-like packets. So waves, even though they're massless, have a particle-like quality to them. That's where we get photons. Photons are just like one particle of a wave, is one way to think about it. They're not actually particles. They don't have physical mass, but they function like particles in the sense that they come in chunks. And then all physical particles have a measurable wavelength. And so this was done by a physicist named de Broglie, this stunning lad right here. And he found that the wavelength of any particle is equal to h, Planck's constant, divided by the mass times its velocity. So, here, m is mass and v is velocity. Because mass is in the bottom, larger particles have extremely small wavelengths to the point where they don't matter. And it turns out that because of this equation, the only thing that is small enough to have a wavelength where the fact that it acts as a wave actually matters is an electron. So remember, an electron is 1/118th the size of a proton. And it's so small that electrons will function like waves. So this leads us to this idea, and we're getting all these different pieces. This is history of science stuff. We're getting all these different pieces. We're putting them all together, and we find that, hey, if you shine a hydrogen lamp through a prism, you don't see a rainbow. So if you shine a regular light through a prism, you'll see the whole rainbow, because a prism will bend different wavelengths of light to different amounts, so it separates different wavelengths. It separates the colors. If you shine a hydrogen lamp through a prism, you get 4 colors. You get 4 lines. And so putting all this together, the wave-particle duality, the photoelectric effect, things like that, and this was what Niels Bohr had a big hand in developing it, but the model that was developed was this idea, this quantized idea of quantized energy, where there are certain energy levels that exist in an atom or in a molecule, and the electrons can only occupy those levels and nothing in between. So my electron can be at n equals to 2, or n equals to 3, or n equals to 1's down here somewhere. N equals 1, 2, 3, 4, 5, 6. I can never have an electron here. Right? Can't have an electron here. I can't have an electron here, right? It could be here, or there, or down here, but it can't ever be anywhere in between. And the way that you see that in the photoelectric effect is that if you don't have enough energy, then the electron doesn't get ejected. Nothing happens. You have to hit a certain threshold. So if you put in enough energy to go from here to here, the electron doesn't move at all. So you have to put in sufficient energy to cross the entire gap in one go, or nothing happens. Okay, so that's the idea of quantization of energy. When atoms are at their lowest possible level, we call that the ground state. And then if an atom at a ground state, which here would be n equals 1, but let's just pretend this is the ground state for now. An electron here, if a photon gets absorbed that has enough energy to jump that gap, okay, you can move that electron up into an excited state. An excited state is just any energy level above the lowest possible one. Okay. Now, you can actually measure these energy gaps. These energy gaps are measurable. You need to worry about that right now, but these energy gaps can be measured. And basically, you say, okay, does this photon have sufficient energy to go from here to here? The lower the n value, the bigger the gap. So you'll see these gaps get smaller and smaller and smaller, right? So those gaps get smaller and smaller and smaller. Okay, and then when an electron relaxes, okay, so I'm here and I relax, so relaxing is going from an excited state to a lower energy state. Doesn't necessarily mean going to a ground state, but generally speaking, all of nature wants to go to the lowest energy state, okay? So it goes down here, it would release a photon of a wavelength corresponding to that gap. So absorbing a photon, you go up. Going down, you release a photon. And the photon that's released corresponds exactly to that energy gap. And then emission spectra show you these energy transitions. So these are the different energy transitions for the hydrogen molecule. So this is H2. So if you look at a hydrogen lamp, this is what you see. Now, if you get up to the n equals infinity level, then the electron gets kicked out. It just leaves. But there are actually a couple different series. You have the Balmer series, which shows us as 4 lines that you can see. So red, blue-green, blue, and violet. Those are the 4 lines of the Balmer series. There are other ones, Passion, Lyman, Bracket, Fun probably. The point is, there are other ones. We just can't perceive these with our eyes. So if you look at a hydrogen lamp through a prism, you're only going to see 4 lines. And if you're doing this in the lab or something, the purple one can be really hard to see. It's pretty faint, but sometimes you can see it. But if you look at other elemental lamps like neon or argon, they look pretty cool. You'll see more. You'll see the heavier the molecule, generally speaking, the more possible transitions there are, because the more electrons you have available, the more different transitions you can have, so the more lines you'll see available. So this leads us into wave properties of electrons. So electrons are small enough that they function as waves. And there are 2 ideas that you probably heard of. One is the Heisenberg uncertainty principle. So you can know how fast an electron is moving, but you can't know where it is, but you can't know both at the same time. You probably don't, unless you're doing physical chemistry, probably don't need to worry about this. But basically, you can know one thing or the other thing. If you know this with absolute certainty, then you have absolutely no idea about this one. And if you know this with absolute certainty, you have absolutely no idea about this one. So the more sure you are about one thing, the less sure you are about the other thing. And this sounds weird. Quantum mechanics often sounds weird when we describe it, but it works out mathematically. Then we have the Schrödinger equation, which again is working off this idea that electrons are small enough to function as waves that state the wave of it states the wave property of an electron mathematically. And again, you don't need to worry about this. The point is, you can describe an electron as a wave, and then if you square that wave function, you describe the electron's orbital. So when we talk about electron orbitals, we are talking about probability fields, where an electron could be, areas where an electron can possibly exist.